All right. Well, I hope you guys are doing well, and um, well, let me. I'm going to do a quick demo. We'll start off with a quick demo of naive Bayes and k nearest neighbors in R. Okay. So I like. I know these are like what you have to do in your exercises for the homework, but but of course in real life we would not actually code it up ourselves. We would just use what R gives us. Okay, so we can use the naive Bayes function. There's probably several naive Bayes functions now, but one of the earlier ones was from this package E1071. This is like some kind of computational group. Whoops, what happened? And the way you would do this is, you'd load up your data, and here we got the iris data set, four variables: sepal length, sepal width, petal width, okay? And then if we ask for help on naive Bayes, okay, this gives us a little bit of information. This fits a standard naive Bayes classifier, assumes independence of the predictor variables, that's the naive assumption, and Gaussian distributions of metric predictions. Okay, so this is basically trying to fit some kind of a series of normal distributions for each numeric variable, which is often what we do in many situations, but in some cases you might believe the numeric distribution not to be Gaussian, and in this case the naive Bayes function is not appropriate. But this is basically what you guys are tasked to do. Your values will probably end up a little bit different than what the naive Bayes function here does, but anyway, the way it works is you just call naive Bayes, and then you give it the formula. So here we want to predict species based on the four predictors, right? Another option is I could just do dot, right? And that would do basically all of the other predictors, but just to kind of write them out, I have this. And then you say data is equal to iris, and this creates your naive Bayes model. Okay, so here my naive Bayes iris model is right here. And what you can do is, now that you have this model, you can create predictions using it. So here, this is perhaps I should subset the iris data set so it's not the full data set. But anyway, basically I trained it on the full data set, so of course the predictions will be good. But maybe I could create like a training to be like a subset of iris, right? Iris, where we sample 150 and 120 of them or something, okay? Okay, well anyway, we could do this, but I didn't. Okay, so anyway, basically we're gonna just ask for it to make a prediction based on these four, and we'll say, okay, based on these four measurements, what do you predict? So we say predict using this model that we've already trained using naive Bayes, and make the prediction here, and it says I'm going to predict setosa, okay, which is the case because if I did iris and I said what is the first one, its true species is setosa. If I say do a prediction where type is raw, then it will give you the vector of values that add up to 1, okay? And here we could do a prediction for all. So I can just say predict using the model for all of our data points. Okay, so this is everything. Basically, use columns 1 through 4. Just don't use the 5th column. Okay, and so this says, all right, this is what I'm predicting. I'm predicting, you know, Setosa and Virginica and versicolor. And if we want to kind of see, you know, how good are our predictions, we can compare the predictions just from the previous command to the actual species label and create a table. And it's mostly pretty good. For Setosa, it's got 50 for 50, and then for versicolor and Virginica, it's made 3 misclassifications for each of those. But not so bad, not so bad. Okay. It's just a coincidence that they have 3 misclassifications for both. It could have been like 2 and 4 over here or something like that. There's nothing that says it has to predict 50 for each column or row. Okay, so that's using the naive Bayes function from package E1071. And I'm sure if you did naive Bayes in R, I think there's a couple other package functions that would work just as well. That might even let you specify the distributions themselves rather than the Gaussians. Oh, let me just kind of do, if you type in NB-IRIS, the output of the naive Bayes for the IRIS data set, it will kind of give you, so here it gives us the a priori probability, so it says 1/3. So this is the priors, okay? And this is based on the fact that there were 150 observations and 50 of them were Setosa, so 50 over 150 is 1/3. Okay, and then the conditional things, I think these are basically the mean sepal length for Setosa and the standard deviation for each of these. So, so yes, you've got to figure out kind of all 24 of these values because you have 4 different normal, each class is total distribution is a product of 4 different normals, right? You got a normal distribution for sepal length, a normal distribution for sepal width, a normal for petal length, and a normal for petal width, and everything's a product of all 4. And then you've got 3 different classifications, so you got a total of 12 different normal distributions. Each of them, you have to predict a mean and a standard deviation and figure that out. Okay, but it does make our life easier because with naive Bayes, you only have to figure out the mean and standard deviation. You don't have to figure out the covariance. Because if we had all 4 in a multivariate distribution of 4 variables, then the covariance matrix would be 4 by 4, and that has 10 unique values to figure out. Because you've got 4 down the diagonal, and then the upper triangle would have 3, 2, 1, so a total of 10. 10 things. It's symmetric, so it's not 16 values, but still, 10 is a lot more than 1. Okay. Or 10 is a lot more than 4. Okay, so that's the naive Bayes classifier, and then for k-nearest neighbors, I'm just using the example that came with this package class. So you load up library class, okay? Here it splits up the IRIS data into training and test. It actually reformats IRIS into an array, a 3-dimensional array. So if we look at IRIS 3, it's got the same 150 observations, except it has, it's a 4 by 50 by 3. I'm sorry, 50 by 4 by 3. So 50 rows, 4 columns, and 3 layers. 1 layer for Setosa, 1 layer for versicolor, and 1 layer for Virginica. So it's an array. So anyway, it just for the training, it decides to make a training data set by taking the first 25 rows from each layer in the array, and it creates our data set train, which is going to be 75 by 4. Okay, so 75 by 4, And then, and test will be the other 15, so it's going to be 45 by 4. I'm sorry. The other 25, not 15. 25, so it did half, the first half to train and the second half to test, okay? So we've got 75 in the training and 75 cases in the test set. And then for k-nearest neighbors, it's going to create a vector called CL, and this is just the labels for our training cases. So we've got S's and C's and V's for the different labels. So I guess Setosa, versicolor, C for color, and virginica. Okay, and so k-nearest neighbors, you take in the training data. So here we'll look up the help for K and N. So you have to provide it training data and test data. Okay, so the training is basically our 4 variables, and the correct answers are listed in class in CL. So we've got train and class, and then our test cases go here. So it's the format's a little bit different. You're not creating a model like in naive Bayes, but you're just going to do predictions for your test data cases. So you have KNN, the training data with the classifications for the training data. Then you have your test cases. You say K is equal to 3, and then prob equals true will return the probability votes, okay? And so if I run this, then it returns back. These are the predictions, okay? So Setosa, versicolor, it gets some of these wrong. And you can see, you know, what was the probability associated with each of these things, not the probabilities, the votes, okay? So we have K equals 3, and so with K equals 3, you know, what proportion got Setosa votes? 100%, 3 out of 3 got Setosa votes. But for observation 28, whichever one that is, only 2/3 voted for whichever case that was, okay? So that's K and N. You can kind of mess around with this and see, you know, what would happen if I did K equals 1, and you can see how the predictions go versus K is 5 or something, and so in some of these, 66, I don't know how that works. Okay. I'm not sure how we're getting a 2/3 vote when we have K is 5, but anyway, well, you can alter the K for K nearest neighbors here. Okay. I'm not sure. I don't know what this is. Okay. The other ones make sense, right? 80% or 60% of the votes were for a certain class. Maybe something weird happened here, but I don't know. Okay. So that's, you know, that's K nearest neighbors in the class data set or class library, and of course there are probably more things there. Okay, did everyone sign in with the attendance poll? Yes. Go ahead and click close here. 22. That's a little bit suspicious, but okay. Well, there's no way there's 122 of you here, but okay. So anyway, that's the quick demo of naive Bayes and K nearest neighbors in R. I want to this week I'm going to introduce PCA. Okay, and PCA is called Principal Components Analysis. Okay, and this is this falls under the topic of unsupervised learning. It can be used for classification. It can be used for not classification, for clustering and for dimension reduction, okay? So this falls under, quote, unsupervised learning. What just happened? Okay, unsupervised learning, in that unsupervised learning means we do not provide, quote, answers. So there's no like objective function, there's not a loss function that we're trying to minimize or a likelihood function that we're trying to maximize. We're just searching for kind of structure within our data. And principal components analysis, this is a way for us to look at a data set with many dimensions, okay, and try to reduce it down to a few dimensions that capture the most amount of information, okay? So kind of the big idea is we have a data set with many dimensions, or in this case, many columns. Okay, but many of these columns might have a lot of kind of collinearity. Okay. Columns may exhibit collinearity. And the idea is, can we reduce this data set that has many dimensions? And can we reduce the data set of many dimensions into a data set of fewer dimensions that still, quote, capture the, I don't know, whatever we might want to call the essence of the data. And so, so here's an example. I don't have the data on me, but so let's say so in the Olympics, there's different track and field events, and you know there's like decathlon and heptathlon, and I think we happen to have data from what we'll call Olympic heptathlon. Okay, so there's 7 track and field events. Okay, things like javelin and, you know, like the 100-meter sprint and, I don't know, like a 1,000-meter race. I don't know, I'm making this up, okay? And what else? Long jump. Okay, the 7 events, okay? I don't know what they are, all right? So, you know, And so each athlete will have 7 values recorded, right? You're going to have like, you raced it in this amount of time, and and there's like hurdles, right? Okay. Okay. What are they? Okay, well, anyway. So each athlete, shot put, right, has 7 values recorded. Okay. But this isn't 7 different events. This is one Olympic thing, right? We have we have separate events for these things, but at the end, there's going to be a gold medal winner for heptathlon, right? And there has to be some kind of ranking system that basically has to combine all 7 values into one dimension, okay? Into one dimension that says this was the best performer and this was the worst performer, okay? So to award medals, we must reduce our data from 7 variables to 1 variable to provide a ranking. Okay. We have there's other examples, okay? So a very simple form of dimension reduction is, so let's say you have SAT exams. And when you guys took it, were there like 3 parts or 2 parts to it? 3, right? I don't know. There was like the verbal, and then the math, and the writing, right? Okay. And you could get 3 different scores, but we also have dimension reduction, and you just have a total score, right? And this is a very simple dimension reduction. We just add the 3 scores together. And so someone says, my total SAT is, I don't know, 2,000, okay? And you'd be like, oh, that's pretty good. But, you might say like, okay, what were your individual component scores, and you want to break them out or something like that. But overall, there's still going to be some general correlation between these things, right? Generally, so, in the upper echelons, we do start to see the things separate out. But if we looked at, like, if we forced everybody in the country to take the SAT score, or SAT exam, generally, students who score high on one section will generally score high on the other sections, okay? And generally, students who perform poorly on one section will generally perform poorly in the other sections, okay? It's not the best predictor, and that's why we have 3 different dimensions. But, if you see someone who has an overall score of 2,000, you can predict something around 650-ish for the 3 different components, right? Something, okay? And, it might be that their math was 800 and their verbal was lower or something like that. Of course, that happens, but overall, higher scores from one subject. So, can we effectively reduce the dimensions in our data set, right? Okay, so this is kind of what we want to do. Okay, so let's take a look. So the idea is, here's just a 2-dimensional example, okay? So you might have something like this. And so this is our data, okay? And can we reduce this to one dimension? Okay, if we had two-dimensional data and we reduced it to one dimension, basically what we would do is we would run a line through here, and then we would get see, where do these things line up against okay, and so now does this even work? I don't know how to rotate. All right, I give up. Cancel. Okay. Basically, we reduce this to just a single dimension. Okay, and so all of the data points basically get put on this thing overall, and we would just have points along here. Something like this, right? And then we could try to then reconstruct the original data. But now that it's been reduced to one dimension, you know, your reconstructed data will just remain in a single line. Okay? And so now you have all the data points kind of along here. Okay, and so basically these in our data, this guy and this person, they get reduced to the same location up on here. Okay, so they are, because we used to have two dimensions of information and we reduced it to one. These people appear to have the same score in the reduced data set. And that's the trade-off in PCA is you used to have many dimensions of data, okay? But maybe that was too much information, and so you said, well, I want something simpler, and so you get something simpler, okay? But of course, when you ask for something simpler, you lose information, and some of the subtle differences, say between these two people, are going to be lost. And that's the cost of summarizing data or dimension reduction. But I think that's okay, right? So for example, in the heptathlon, we're going to just rank them from best to worst, right? And the gold medal, there's the gold medal athlete and the silver medal and the bronze medal. And, you know, maybe the bronze medal athlete grumbles and says like, oh, I would have gotten the silver medal. I should be getting the silver medal because I performed way better in the long jump than the silver medal guy, right? And that might be true. But maybe overall, everything else, if we looked at the dimension reduction or whatever, the bronze medal comes in third place anyway or something, okay? I think they said bronze medal winners are happier than silver medal winners because silver medal winners feel like they lost the gold, whereas bronze medals are like just happy to get a medal. Anyway. I'm just happy to be here. All right. Okay, let's, today was just kind of a high-level introduction to this topic. Here is a cool website that's no longer updated, much to my disappointment. It's called Satosa.io. It's clearly a play on the Iris dataset, right? Satosa.io, and then if you go to EV/EV, it's called Explain Visually, and they have a bunch of cool stuff, but they haven't updated it in a few years. It's not since 2015, but so some of these are very cool, and we'll take a look at principal components analysis. Okay. All right. So here it says, first, consider a data set in only two dimensions, like height and weight. This data set can be plotted as points on a plane, and that's what we have, okay? But if we look at the variation, it says PCA finds a new coordinate system in which every point has a new x and y value, okay? These axes don't mean anything physical, but they're combinations of height and weight. So we create linear combinations, okay? And so this is the original data, and it finds kind of this axis that would say this is the best way to reduce our dimensionality, okay? And so the first principal component is the direction that captures the most amount of variation, okay? So it says, you know, if we plot these points on their x-axis, we have, you know, one right here, and here, and here, and here, and so there's quite a bit of variation on x, and we look at their values on y, there's quite a bit of variation on y, okay? Once we do principal components analysis, you know, our first principal component will capture the most amount of variation in the data set, okay? So it's basically just a kind of, we're taking this and we're reorienting our data so that along our first principal component we have a lot of variation. But then if we look at the second principal component and just see where they line up, they all line up very close to 0. And so there's very little information that's lost in this case. And so it looks like this, okay? With this thing, I can actually drag the data point. It's kind of tricky to do here, okay? So here, if I drag this middle data point, it doesn't actually affect the principal components direction very much, okay? We can still see everything ends up this way, but if we look at the variation in the second principal component, we see that this one data point displays a bunch of variation, right? And then if I pull it so far, okay, then you can see it actually affects the orientation of the principal component, okay? So it's trying to capture the direction that maximizes the variation. So if I were to kind of bring all of these points in this way, and then pull this one out over this way, and pull this one out over this way, then this red direction is the direction that captures the most amount of variation, okay? And we can see how it reorients the graph this way, and so the most amount of variation is captured along the red axis, and then the other axis that's orthogonal to it captures a smaller amount of variation. So PCA, what it tries to do is it tries to find the axis that captures the most amount of variation in the data, okay? And, you know, if you have something like this direction still captures the most amount of variation. Some of the other information is going to be lost if we reduce it down to one variable, okay? So if we just said, let's reduce everything to the first principal component, then we will get this down here, but the variation captured in the second dimension will be lost. It can be done in 3 dimensions, okay? And so here we have a data set of 3 dimensions kind of rotating around, okay? And here we are, so this is where the kind of the cloud of data points in the X, Y, and Z. And when I click Show PCA, what it's going to do is it's going to reorient the axes for X, Y, and Z such that the red arrow will point in the direction that captures the most amount of variation. Then the green arrow will point in the direction that captures the second most amount of variation, and then finally the blue arrow will capture the direction that has the least amount of variation. So after I click Show PCA, what you will see is that the red axis should show the most variation, green will show the next amount, and then blue will show the least. So, and it's just reorienting the structure of the kind of the axes. Okay, so I'm going to click this, and so it does that, and so red definitely has the most amount of variation, and green has some, and blue has less, although green and blue look almost the same here. But you can see how the arrows have changed their orientation. Okay, and so if we look at the red and the green, this captures the most amount of variation, and yes, blue is kind of the leftover variation, but if we look at the blue axis, we're not losing too much information. And so here we can, just with the red principal component, we can see the cluster nature of our data. We can see that there are 3 individual clusters appearing. Whereas when we looked at just the X and Y and Z information here, it's not clear that there are 3 clusters in our data. So that information is lost when we looked at the original data set. After performing principal components analysis, we can begin to see the cluster nature of this. Okay. Of course, when we plot it all in the graph, we can see the clustering nature. It's hard to visualize anything higher than 3 dimensions just because our experience of reality is only in 3 dimensions. So plotting things higher than 3 dimensions is hard to do. But here we have some data with 17 dimensions, okay? And here we're looking at different parts of the United Kingdom. So the United Kingdom consists of 4, what would you call them, countries within the United Kingdom. There's England and Northern Ireland, Scotland, and Wales, and things like that, and they have their own dialects and stuff. But we asked, how many alcoholic drinks do you consume, and how many other beverages, and I don't know what carcass meat is, but I think that's like sausage, I don't know, okay, and cereals, and fresh fruit, and fresh potatoes, and other meats, and other vegetables, and processed potatoes, and processed vegetables. And we asked, tell me, how much do you eat? How much of these things do you eat? And this is their responses for these 4 different things, right? And you're just like, okay, everybody eats lots of cereals, everybody eats lots of soft drinks. Looks like Northern Ireland consumes fewer alcoholic drinks than Scotland and Wales and England, but that's what we have, okay? Once we perform principal component analysis, this is what we find. We find Wales, England, and Scotland show up on one end, and Northern Ireland, this is the one that's like most different from the other 3, okay? So which of these are the most different? I don't know. Is that because they're on their own island? I don't know. So principal component analysis kind of says, Northern Ireland is a major outlier. We create something called, and we can look at the first 2 principal components, okay? And you can see principal component 1 is just everything gets put onto this axis. And again, so we've reduced our 17 dimensions down to 1 dimension if we decide to keep 2 dimensions out of the 17, okay? And it's not keeping, we're basically casting a shadow in such a way to do this. This is what we have, okay? And if we look, what we will actually notice is if we study how much how many fresh potatoes do they eat? Northern Ireland consumes a lot more potatoes at 1,000 versus, you know, the other ones at, you know, 720 and things like that. The alcohol drinks also kind of factors into a place here. So, yeah, the idea of principal component analysis is we are reorienting our data and projecting our high-dimensional data down into lower dimensions. And what we want to do is, so just kind of a recap. So what PCA is, we have high-dimensional data. Okay, and we reorient our axes so we can project our data down to fewer dimensions. Here, another analogy is when you cast a shadow, you are projecting light over a three-dimensional object to create a two-dimensional shape, okay? So if you have like a hand, this is my, right? And don't laugh, okay? So here's your hand, and when you cast a shadow, you get something that looks like this, right? Okay. And so when you cast this shadow looks like a hand, okay? Okay. On the other hand, if the data is oriented differently, okay, such that your hand is okay like this, and the light's coming down, it's also possible that your hand looks just like this, right? The shadow could look like this if you orient your hand this way, okay? So this is another, it's a perfectly valid projection of the data, but you lose the structure here, okay? Another valid projection, okay? But structure is lost. And so what principal components analysis wants to do is it wants to find the projection that will maintain the structure that exists in our data, okay? And so on Wednesday, we'll explore that by talking about, we want to find the projection that maximizes the variance in our data, okay? So we'll end here for today, and we'll see you guys on Wednesday.